Now, what we've really seen is that this is the form for the magnetic energy density. If we make a series of guesses about how energy is stored inside of our inductor, and also we only really have a result for one particular case, we really shouldn't have too much faith in this relationship at this point unless we believe that we can truly reason directly by analogy. We had a formal proof for the electric field energy storage, and since the magnetic formula looks so close, we might think that this really is the final result. But if we really want to prove this rigorously, we need to consider the most general type of situation and then prove that energy always is conserved. So I want to consider now how we would construct a general proof for the conservation of energy in the electromagnetic case. Now, for that to work, we are definitely going to have to use everything that we know about electric and magnetic fields. The way we're going to carry this out is we're going to begin by imagining the most general possible situation. I want to imagine considering energy in some very complicated system, something maybe that combines everything that we know in full generality. So let's imagine some crazy system, right? I'm going to have maybe some big magnet here that has his magnetic field lines, and within that magnet there's going to be a wire, say, that's moving through that magnetic field, and that wire is maybe generating an EMF that then is being used to put charges on some kind of a capacitor. So there's going to be some electric field here inside my capacitor, and maybe there's some point charge. We'll make some fully general thing, right? Maybe there's some point charge that's going to be traveling through this electric field, and it might have its, maybe it's a negative charge, it might have its trajectory changed and its kinetic energy changed. And then I might also use the power that I'm generating through this magnetic field circuit also, not only to drive this capacitor, but it also might be part of a circuit that has an inductor in it, which is then generating an additional magnetic field over here. And then finally, who knows, I might connect to a resistor, R, right, where there's some further interactions of moving charges and particles where heat is then generated, and then that might be here completing my circuit. And what I'm going to do is I'm going to take this entire system here with every possible imaginable thing happening, the fully most general situation, and I'm going to put it into some kind of a very large box, and I'm going to consider then all of the energy associated with this box. So it's all in some giant volume, capital V. Now, if energy truly is conserved, what we are saying then is that if we look at the time derivative of the total energy that is stored in this volume, right, that total energy in that system, and I look at its time derivative, that is going to have to equal, right? Now that total energy stored in here comes in two forms. There are electromagnetic energies, and those are the ones that we think we now have the formulas for energy stored in electric and magnetic fields. And then those energies can come out of the electromagnetic field and manifest themselves as work and heat and changes on trajectories and particles. So there is electromagnetic energy, which I'm going to add up here as my total energy. And the rate of change of that, if I'm dissipating power, if I'm getting power out of the system, is going to be minus then any power that comes out of the system, any work that these fields do on any moving charged particles. And we've already discussed how we know this would be a minus sign because we're talking about power coming out. Positive power out means decreasing the total energy stored in the system. Now, in terms of the total energy stored, we believe now that we have a complete field theory. So we believe then that this can be decomposed into the total energy stored electrically plus the total energy stored magnetically. In fact, if this whole framework doesn't work out, it might become evidence for us that there are some additional fields that yet we have not yet discovered. So in terms of these total energies, the electric and magnetic components, We have actually formulas for those because we know their various densities and we know how to integrate those up. We need, though, also to have a general formula for power. So let's think what the power coming out of the system would have to entail. So the power that can come out of the electromagnetic fields in this volume that we are talking about, right, should come out then as in the form of work. Any work that our fields might be doing on any particles that would be traveling through the system. So that would involve then a sum over all particles I of the forces that the particle I happens to be feeling, dotted then with the velocity of the ith particle. So these are going to be any electromagnetic forces that are acting on particles traveling with different velocities. And this is just the standard formula for power. Summing over all the particles in here, that's all the ways that energy could get out of our electromagnetic fields in this region, unless, of course, we're wrong and there's some other way electromagnetic energy could get out of this volume. So I'm going to leave open the possibility that there is some other way energy could get out of here. Our hope is that when we carry out the proof, eventually perhaps we can prove that this term here is 0. Now, let's focus on this term here. This term is the power that's coming out because we are acting on charges. So I'll call this P out sub Q, the work done on any charges. Now, this power that comes out of the electromagnetic field on any of the given charges, we know then is going to be the sum over all the charges. And we know the formula, of course, for force, right? On any charged particle. The force that comes from the electromagnetic field. It's just the charge on each particle, Q sub I, times then the electric field that particle happens to be feeling, which would be the electric field measured at the location of my particle. That's the electric force that I've written down here so far. Of course, next we have to add on the magnetic force, which goes like Qi times Vi cross the magnetic field at the location of that particle. And then this whole force that we've just calculated has to be dotted with the velocity of the particles, dot Vi, like so. Now, in terms of the magnetic field energy, of course, there's a very interesting result. We know that the cross product of V and B has to always be perpendicular to both vectors, and in particular, it has to be perpendicular to the velocity Vi. But if I have a vector perpendicular to Vi, and then I calculate the dot product with Vi, what's going to happen is I'm going to get the cosine for the dot product, but that cosine for the dot product from this term is going to be at a 90-degree angle with respect to Vi, which is going to give me 0. So this term here, at least, I know, vanishes. There's no work associated with the magnetic field. It can't actually do any work on any moving particles. So all that is left then are these terms from the electric field. And these we can simplify a little bit further for ourselves, because if we sum up over all the particles I, we've got Qi, the electric field, dotted with Vi. Now the dot product is commutative, so of course I can switch the order. So I can rewrite this as the sum on Qi Vi, the Q's and velocities of each particle, dotted with the electric field at the location of each particle. And finally, this term itself should look very familiar to us. We've been trained in the past that whenever we see a sum of Qi Vi times something, then instead of thinking of summing over, all the different particles, we can always directly relate this to currents that are flowing. The way we usually do this, if we're thinking of wires, is that sum of Qi Vi, of course, becomes the integral along the wire, IdL, and then multiply by whatever the other quantity is. In this case, it would be the electric field. But that is if we're doing wires. More generally, the more general expression says that instead of integrating along a narrow wire, we could instead integrate across a volume, and then IDL gets replaced with an integral then over volume of whatever current densities we have times the volume element dV, and then dotted with the electric field. And that's a very nice general formula that works over any given volume. So our plan is going to be to integrate then over our volume with this complicated experiment of simply the dot product of the current densities J dotted with the electric field, whatever current densities might exist in our various wires, our resistors, our capacitors, anywhere within that given circuit. So this then gives us a nice result for the power out associated with work done on particles. That then, combined with our knowledge of how to calculate electric and magnetic energies, allows us then finally to test this idea of whether we can build a fully consistent field theory that actually conserves energy.